Hi everybody. So I'm going to use this tutorial to introduce the idea of an electric circuit. And we're going to transition from static electricity and Coulomb forces that exist between charges or among charges, and now talk about the energy aspect that you ultimately can get from it. So it's a big jump from what we learned in statics to what we're about to do now, but that's what the AP asked for. In year 2 of physics, if you take that, we'll go into more detail about electric fields and electric potential. But for right now, I'm just going to give you a very basic overview of it. And I'm going to try to link another video from Flipping Physics that explains electric potential in a little bit more detail, just so you have a better idea of what it is and how it fits into it. So I'm going to construct a circuit using a simulator, and perhaps we might do a phet lab to follow up with it. And in the process, talk about the energy that you can get from an electric circuit, what it means to be a circuit, what components are needed, and then in follow-up tutorials, we'll look at the measurements that you can make. Okay, so what you see in front of you is a battery. Okay, so a battery is a voltage source. Okay, and we want to talk about what that means, voltage. It's a term you've all heard of before, but very few can really tell you what it is, except that it's associated with electricity. What I want you to understand is your most common voltage source in your life is not so much batteries, but it's outlets in your home or a building. So when you plug into an outlet, that outlet is connected by wires back to a power box, or I should say a circuit breaker box in your home, either outside your home or in your basement. And that's ultimately connected by wires to power lines, be it underground in your neighborhood or along the telephone poles that might be more in an urban area. And that traces ultimately back to a power plant. And at that power plant, something is going on. There's a large electric generator that is creating voltage. And so that voltage is sitting there at your outlet, and it's what it really is a potential. It's technically called electric potential. It sounds a lot like potential energy, but it's not quite the same thing. But for right now, what I want you to understand about a voltage source is that it's our input of energy. Okay? Our input of electrical energy. A battery does something similar to an outlet. It just does it by a different means. Batteries do it by chemical means, whereas outlets, which are ultimately attached to generators, do it by electromagnetic means. Solar cells could be another type of voltage source. But the point is, in order to have electricity and the energy come from it, you need an input, and that input comes with a voltage source. So it can come from one battery, I could connect another battery, and I could up my voltage, right? If I click on that, I see that this by default is 9 volts. And if I click another one, 9 volts. So what I have here is essentially 18 volts of potential. I'll define voltage later, what a volt means, but it's really energy per unit charge. So for every unit of charge that I can get to circulate around, I will get, let's say in this case, 18 joules of energy. In a home, you get about 120 volts. So you get a lot more energy per unit charge, which is needed to power the appliances you normally run. For batteries, you are used for low power devices. Okay, so right now we have a push. So there's our first component. We've got something that's ready to push. Well, what do we want to push? We want to push charges around. And we're using the charges as conduits or a means for delivering energy from our input to our output. Okay, so what I want you to understand about a battery, it is not a reservoir. It's not a source of charge. It's a source of push, an electric field, a force, or energy. They're all kind of similar ways of saying the same thing. So the whole point of setting this up is we want to use the energy elsewhere. So another component we need is a load or an appliance. So in this case, we're just going to have a light bulb. Okay, so I want this light bulb to light up by moving charges through it, and especially the filament part. And what the charges do is they give up the energy they get from here, and then they just circulate around. Okay, so the charges are like little trucks that carry energy from our input to our output. The trucks or the charges aren't used up. They just deliver the energy and then they go get more from the voltage source. So in order to get from here to here, we need to connect it to, and that's what your wires are for. Okay, so the obvious role of a wire is to simply connect your input to your output, and it can be done over very long distances. That's the beauty of electricity. You don't need a power plant right next to your home. You could have a portable generator, which some of you might have. If the power goes out, But generally, the North American power grid or any power grid around the world is not centrally located, but it's remotely located, and you just distribute the energy via power lines. Okay, so that's the obvious role of wires. Perhaps the less obvious role, but even more important, actually, let me not do something here, is that wires are ultimately where the charges come from. In other words, if the point of the voltage source is to push charge around, the charges don't come from the battery, even though there are charges in the battery, just because everything has charges in them. It's in the wires. And wires are generally metals, and metals are metals, and they're good conductors because of those sea of mobile electrons you learned in chemistry. Okay, so I just want to add a switch here. So the three main components, like I said, are the voltage source, the wires, and the load. So a switch is a component, but it just serves as a way of breaking it. So what I want you to notice now is that nothing is happening even though I've got a battery here with potential. So you do not get a delivery of energy until the circuit is complete. And a complete circuit means we have to connect ultimately the positive terminal, which is right here, to the negative terminal. And so you have to do it in a loop. And between the positive and negative is you want a load, because we want to deposit the energy here. If I were to take this load out and just connect here to here, I would still have a circuit. When I close this, oh, I got a fire, okay? A little bit extreme here, but the point is we have what is called a short circuit. In other words, the battery is not only our input, but it's also our output. The energy is being delivered to here in the form of thermal energy, so it gets really warm, and the wires will get really warm, and in a 120 volt source in your home, that will cause a fire. So you always have to have a load where the energy is deposited. Okay, and we're going to learn, it doesn't have to be just one load, you can have multiple loads, but we're going to start with the simplest possible case. Okay, so that really is the idea. Now, here's where things might be confusing. If I close a switch, there you go. What we have are electrons are moving from, well, it's technically electrons move, but at the AP course level, we do the opposite. We do conventional current. In other words, we assume the positives are the one that are delivering the energy. It's a there's historical reasons for that. Essentially, when we first guessed what charges move in the 18th century, we guessed it was the positives that moved. It wasn't about another 100 years later, but we figured out it was actually the negatives that move. And how we figured that out is fairly abstract, and we've got to understand magnetism to understand that. Anyway, so this is how we're going to treat it. We're going to pretend the positives move. So right here, the positive terminal is at high voltage. In this case, that's at 18 volts. So let me bring out a voltmeter, because we'll eventually do it in class. So if I put a voltmeter right here, and I put the other voltmeter right here, I see that I have 18 volts of potential. So this part is at 18 volts. This part is at 0 volts. Okay, let me just close this switch now. So even when I open the switch, I still have 18 volts of potential. So this is like being at a high ground. This is being like at the low ground. And the goal is the electrons are, or excuse me, the positives are falling, not literally, but in a sense falling from here to here. And so when they fall, or where they do the falling is across here, they give up the energy, like water going over a waterfall. So if that's still a little bit confusing, let me show you this. If I look at the potential between these two spots, you see it gets 0. So what that means is the potential between here and here is 0. There's no energy potential there because this is at 18 volts. And since the wires are ideal, meaning they have no resistance, this part is at 18 volts. So the difference between here and here is 0. And that's what a voltmeter reads, is the difference in potential. If I move to right here, it's still 0 because they're both on the high side, of the positive side of the circuit. But as soon as I go across on the other side of the load, okay, let me make a connection. Oh, it's still 0 because of this open part here. So let me close this. So now we see that there is a drop from the positive side to the negative side. And then what happens is, if there's no potential anymore, the battery acts like a pump to pump up the energy. Okay, so it pushes the charges uphill to give them energy. How does it push it up here? That's the chemistry behind the battery. We don't have to know about that. And so we're constantly delivering energy right there. The light bulb gets warm. The filament gets hot enough to start glowing. And you have basically electrical energy here and thermal energy here. And since it's so hot, we also get a little bit of light energy. That's a traditional incandescent bulb. In an LED, it would be all light pretty much. Okay, so if we measure potential voltage about a battery, we have to eventually learn what to measure about the flow of charge. Okay, so it's not the amount of charge that matters, but it's the rate at which the charge is flowing. In other words, charge per unit time. And that's called electrical current. It's very similar to current in a river. You can have a fast-moving river, but if it's a very narrow river or a stream, you don't have a lot of current because there's simply just not a lot of water flowing by. And that's what, for another analogy, that's why Niagara Falls is considered one of the natural wonders of the world. Not because it's a particularly high falls, it's because there's so much water going over a particularly big drop. That makes it pretty spectacular. So it's the volume of the water which is akin to electric current. Okay, so what we want to understand is the current, and I'm going to use a cheat here. So how you connect an ammeter is not done by what I'll show you. I'm not sure what this device, how it literally works, but if I just put it here, I see I have a current of 1.8 amps. I put it here, 1.8. If I put it here, it's still 1.8. So we just want to reinforce the idea that as charge flows through the light bulb, it's not used up. You can't create nor destroy charge, so I have 1.8 amps everywhere in the circuit. Okay, so I'm going to finish up with one other analogy to kind of introduce. And I may use this analogy again in the notes, but I don't remember. Let me just close the switch. So a good analogy, besides a river system, so let me go back to the river system. So in a river system, you can think of the battery as, here is the high part of a waterfalls, this is the low part, where it pools. And so what the water wants to do is fall from high to low, but we don't do it directly in this direction. I'm sorry, I can't draw an arrow. It falls over, so the actual falls occurs at the load. Okay, so we're at high potential. So when we turn on the circuit, this is like water's flowing on the high part of the river, and then it goes over the falls, gives up the energy. It has no potential. It still flows there, and then there is some sort of pump that pumps it back up. In nature, it's the sun that acts as the pump to get the water back to the top of the falls through the water cycle. Or you could have a literal pump. Another analogy that is sometimes useful is think of this as a bicycle system, where this is the pedals, that's your input of energy. This is the back tire, which is your output of energy. So to get from the input to the output, you got to connect them together. That's what a chain does. So if I close the switch and I ask, which charge moves first, the temptation is to think that charge comes from here, flows through here, and then ends up back there. But when I close this, notice there's no sequence. It all happens at once. So think of the charges like the links in a chain, and as soon as you start pedaling, all the links move at once. It just needed a push to get them all going. That's what the voltage source does. But if I pedal my chain and it's broken at some link, like here, nothing's going to happen. So you have to have a complete circuit for the energy to be delivered. As soon as you break that circuit, like let's say your chain breaking, not that that happens often, you're not going to get any energy delivered. Okay, so hopefully that helps you give you context for all the details you're going to learn next. You're going to learn about voltage, current, and then ultimately about power. Right? We want to calculate how much energy is delivered, or the rate that is delivered in power. And then we're going to talk about meters, how you actually measure voltage. We'll do this in class with a voltmeter, and then ultimately with a real ammeter, because it's not so simple as just to place it here or here. Ammeters are a little bit more of a pain to put in a circuit, but we'll learn about that.